All right, welcome everyone. Today we are going to pull back the curtain on the secret language of motion. There's this invisible set of rules that governs literally everything that moves, from a simple wrench in your hand all the way up to the most advanced robots we're dreaming up for the future. This isn't just a physics lecture. This is the bedrock of how we design machines.
So, let's start with something you've probably all seen, maybe even used. A pair of vice grips. It looks pretty simple, right? But the way it transforms just a light squeeze from your hand into this incredibly powerful clamping force, well, that's a perfect little piece of mechanical magic. This one tool holds the key to understanding machines that are a whole lot more complicated.
I mean, really think about that for a second. How does that little bit of effort from you generate a force so huge you could never create it on your own? What is the secret that's not only multiplying your strength, but also locking it in place? This, right here, this is the fundamental question that drives the entire field of mechanism design. Okay, so to really get this, we have to see that this principle, this idea of controlling motion and force in a very specific way, is absolutely everywhere. It's kind of like the hidden architecture inside some of the most fascinating and complex machines ever built. Just take a look at these two. On the left, you've got this massive walking vehicle, and on the right, a mechanism designed to flap wings, just like a bird. I mean, they couldn't look more different, but they are built on the exact same principle as those pliers, using a carefully designed structure to turn a simple input into a really complex and really useful motion.
But here's the thing. These two machines are solving fundamentally different types of problems. The walking machine, that's all about something we call path generation. Its one and only goal is to make a single point, the tip of the foot, follow a very specific path. The ornithopter, though, that's a motion generation problem. It has to control the entire wing's complex movement, both the flopping and the rotation, to generate lift. So one's about a point, the other is about a whole object.
So how in the world do we as engineers actually describe this stuff, let alone analyze it and design it from scratch? Well, we need a formal language. We need a framework for the geometry of motion. So let's dive into what that looks like. Okay, first things first, let's get our terms straight. A mechanism, you can basically think of it as the skeleton of a machine. It's a collection of rigid bones, which we call links, that are all connected by joints, and its entire job is to take motion from a source, like a motor, and transmit it to an output in a very precise, very controlled way. And the science we use to study these skeletons? That's kinematics. Kinematics is the study of the geometry of motion. We're concerned with things like position, velocity, and acceleration. Now, what's really crucial here is that, for now, we're not worried about the forces or torques that are making things move. We're just looking at the motion itself. It really is like geometry, but with time mixed in. So what are these mechanical skeletons actually made of? Well, it all boils down to two fundamental building blocks: the rigid bodies, which we call links, and the joints that connect them together. And look, if the links are the bones, then the joints are absolutely the most critical part. You can almost think of them as the DNA of the mechanism. A joint's entire purpose is to define exactly how two links can move relative to each other. It allows certain motions, and it prevents all the others. Now, joints come in a few basic types, and this chart here shows the 6 most fundamental ones. We call them lower pair joints. Like a simple hinge on a door or a piston sliding in a cylinder. The reason they're called lower pairs is because the parts that are connected make contact over a whole surface, and that, it turns out, is key to making them durable. And this distinction is so important. Lower pairs, they spread the load out across a surface. Higher pairs, on the other hand, things like a gear tooth or wheel rolling on a track, they concentrate all that force onto a tiny point or a line. And that creates way more stress and causes them to wear out a lot faster. So you can see why, for machines that need to be robust and last a long time, designers try to stick with lower pairs whenever they can. All right, so we've got our building blocks, links, and joints. The next big question is, how do we put them together and actually predict how the whole machine is going to behave before we even build it? We can do this by calculating a property we call mobility, which you'll also hear called the number of degrees of freedom. It's just one number, but it tells you the absolute minimum number of inputs, like motors or pistons, you're going to need to completely control the entire mechanism. It's really the key to understanding how constrained or how free a machine's motion is. And this right here is the tool that lets us do it. This equation, sometimes called the cut-spot criterion, is one of the most powerful concepts in all of kinematics. I know, it looks a little intimidating, but it's really just a simple recipe. You tell it the number of links and the number of joints in your design, and it spits out the mobility. Simple as that.
Let's try it out. Here we've got the most classic mechanism of all time, the 4-bar linkage. Okay, we have 4 links. You have to remember to count the ground, the fixed base, and 4 simple one-freedom joints, which are just hinges. We plug those numbers into our formula, and out pops a mobility of 1. And that tells us we only need one input, just one motor, to drive the whole thing in a perfectly predictable path.
Okay, now look at this more complex machine. Let's count them up. It has 7 links and 8 joints. So when we run those numbers through our mobility equation, we find out the mobility is 2. And that tells us instantly that to fully control this thing and get it to do what we want, we would need 2 separate motors or actuators.
And this explains why you see things like the 4-bar linkage absolutely everywhere, from car suspensions to windshield wipers to factory equipment. They are the workhorses of machine design because they hit that perfect sweet spot. They're the simplest possible structures that can generate these incredibly useful, complex motions from just a single easy-to-control input. Now, let's take these fundamental ideas, links, joints, mobility, and see how they apply to the really exciting stuff, modern robotics. This is where it all comes together.
A modern robotic arm, whether it's in a factory or part of a future humanoid robot, is a perfect example of what we call an open kinematic chain. Each segment of the arm is a link, and every single joint is independently powered by its own motor. And this arm has mobility of 6. Think about that for a second. Why 6? Well, any object floating in space has 6 degrees of freedom. It can move forward/back, up/down, left/right. That's 3. And it can rotate about those axes: pitch, roll, and yaw. That's another 3. With a mobility of 6, this robot's gripper can reach any position and any orientation within its workspace. It has the same freedom of movement as your own arm. Or check this out, the Stewart golf platform. If you've ever been in one of those full-motion flight simulators, you've experienced one of these. It uses 6 legs that are all controlled with incredible precision to give the cockpit full 6 degrees of freedom movement. It perfectly mimics the pitch, roll, and yaw of an aircraft. This is kinematics literally creating a virtual reality.
So here's the big idea, the one thing I really want you to take away today. It doesn't matter if you're analyzing a simple pair of pliers or if you're on a team designing a humanoid robot to do our chores. The fundamental language you're using, this language of links, joints, and mobility, is exactly the same.
You see, understanding this secret language gives you the tools not just to analyze the world, but to actually create and innovate and build new things. So I'm going to leave you with this question to think about. Now that you know the rules of motion, what are you going to design?